Amidst our hectic work schedules, let me first guide you through the waters of NVIDIA's ecological moat, CUDA. Actually, every time you speak to an AI, thousands of little elves are working furiously behind the scenes. That's CUDA. Have you ever wondered what happens in those few seconds when you open your phone and say to your AI assistant, "Write a leave request email for me"? It's not magic, nor is there a programmer typing furiously at the other end in that moment of waiting, inside a server. In some data center, thousands of computing units are activated simultaneously. Like a well-trained army of workers, they divide the labor and, in a fraction of a second, process billions of mathematical calculations behind your sentence. The scheduling system for these workers is called CUDA. It's not an app, not a chip, and not software you can download. It's a programming platform that unlocks the full power of GPUs, graphics processing units, the most underrated yet absolutely essential foundational technology of the AI era. What is CUDA? Let's start with what is a GPU. Before we dive into CUDA, let's briefly talk about GPUs. For more details, see my previous video. What exactly is a GPU? Why has the AI era suddenly become dependent on it? Inside your computer, there are two main types of computing chips: the CPU, Central Processing Unit, and the GPU, Graphics Processing Unit. If the CPU is like a top-tier chef, experienced, incredibly responsive, capable of handling all sorts of complex tasks, but alone in the kitchen, then the GPU is like a massive central kitchen with thousands of assistant chefs. Each assistant may not be as skilled, but with so many hands, they can chop, stir-fry, and plate simultaneously, achieving staggering efficiency. GPUs were originally born to render game graphics. An image consists of millions of pixels, and the color calculation for each pixel is independent and doesn't interfere with others, making it a naturally perfect scenario for parallel computing. That's why GPUs evolved with extraordinary parallel processing power. But here's the question: if GPUs are so powerful, what else can they do besides rendering games? CUDA, Compute Unified Device Architecture, is NVIDIA's answer. Simply put, CUDA is a platform and programming model that lets developers use GPUs for any kind of massively parallel computing beyond just graphics. With CUDA, scientists can simulate protein folding, engineers can train AI models, and financial firms can run risk calculations. As long as your task can be broken down into many small tasks that can run simultaneously, GPU plus CUDA will make it fly. Let's rewind to 2006. That year, NVIDIA made a decision that seemed somewhat fantastical at the time. They opened up the GPU's computing power so that ordinary programmers could use it. That was the birth of CUDA 1.0. Before that, GPUs were like modified race cars, astonishing performance, but only game developers knew how to drive them. Academic researchers wanting to use GPUs for scientific computing often had to pretend they were rendering graphics, tricking the GPU into working through graphics interfaces, cumbersome and awkward. CUDA's emergence was like NVIDIA handing over the keys to that race car to everyone, along with a driving manual. A quick timeline: 2006, CUDA 1.0 released. The era of general-purpose GPU computing begins. 2012, AlexNet trains a deep neural network on GPUs, crushing all competitors in the ImageNet competition and igniting the deep learning revolution. 2017, the transformer architecture is born. The retention mechanism enables AI to understand long texts, paving the way for large language models. 2020, GPT-3 bursts onto the scene, trained on nearly 10,000 GPUs over several weeks. 2022, ChatGPT is launched. CUDA-powered AI inference reaches every ordinary user for the first time. 2024, NVIDIA's market cap exceeds $3 trillion, surpassing Apple to become one of the world's most valuable companies. Behind every milestone, CUDA is the silent, indispensable key player. How does CUDA work? Understanding it through a factory assembly line. This is the most technical part of the article, but I promise it won't give you a headache. Imagine a toy factory gets a huge order: produce 1 million building block parts. The CPU way. Serial 1 master craftsman makes part number 1 all the way to part number 1 million, each one crafted meticulously, but it takes a very long time overall. The GPU way. Parallel. The factory has 4,096 assembly lines, working simultaneously. Each line handles a small batch of parts. Although the worker on each line might not match the master craftsman, Having 4096 lines running at the same time is a game changer in efficiency. CUDA is the management system that coordinates these 4096 assembly lines. Inside CUDA's world, there are a few core concepts: thread, the smallest execution unit. Like a single step for one worker. A modern GPU can run tens of thousands or even hundreds of thousands of threads simultaneously. Block, multiple threads form a block, where they can share data and collaborate, like a small team. Grid, multiple blocks form a grid, constituting a complete computing task. When you run an AI model using CUDA, the process roughly goes like this. Break down one layer of the neural network's computation into tens of thousands of independent tiny operations. Assign those tiny operations to tens of thousands of threads on the GPU. All threads start working at the same time, each handling its own little piece. Gather all the results to get the output of that layer. Repeat the above steps until the entire network forward pass is complete. In this way, neural network training that might have taken days is compressed into hours or even minutes. Why is CUDA so crucial for AI? Here's a key insight that many people don't realize. The essence of deep learning is massive matrix multiplication. The model at the GPT-4 level has over 1 trillion parameters, and the number of multiplied operations required for a single forward pass is astronomical. This computation has a beautiful property: each calculation is almost completely independent, making it naturally suited for parallel processing. No matter how fast a CPU is, it can only handle a dozen or so cores simultaneously. A high-end GPU like the H100 has over 16,000 CUDA cores, plus tensor cores specifically optimized for matrix operations, making it hundreds or even thousands of times faster than a CPU for such tasks. CUDA plus GPU equips AI researchers with a tireless mathematical superfactory. Without CUDA, deep learning might still be stuck in the ivory tower of academia, not because the theory was lacking, but because there simply wasn't enough computing power. The ideal would have remained empty talk. It's precisely because CUDA made GPU computing programmable and accessible that we saw the deep learning explosion in 2012, followed by AlphaGo, GPT, Sora, and the AI assistant you can summon at your fingertips today. Real-world applications of CUDA. It's everywhere. You might think CUDA is far removed from your life, but it has quietly seeped into every corner of your daily existence. Ray tracing in games. When you see reflected lights on the floor or rippling water on a screen in a game, that's ray tracing technology at work. CUDA enables GPUs to simulate the physical propagation of light in real time. Each frame is the result of billions of light calculations. Medical imaging diagnostics. The raw data generated by a CT scan is a messy pile of numbers that requires massive computation to reconstruct into a clear 3D image. Most imaging workstations in hospitals are equipped with GPUs, using CUDA to accelerate image reconstruction, allowing doctors to get diagnostic results faster in emergency scenarios. This can be the difference between life and death. Large model training and inference. ChatGPT, Gemini, Claude. All the large language models you've used require hundreds or thousands of GPUs working together for weeks during training. Every time you ask an AI a question, GPUs are also performing real-time inference computations in the background. Without CUDA, all this would be too slow to be usable. Accelerating scientific research. DeepMind used GPU plus CUDA for protein structure prediction, AlphaFold, solving a 50-year challenge in biology by predicting the structures of over 200 million proteins, with profound implications for new drug development. Meteorologists use GPUs to simulate atmospheric movements, making weather forecasts more accurate. Physicists use GPUs to simulate particle collisions, exploring the fundamental laws of the universe. The rise of autonomous driving. Self-driving cars need to process massive amounts of data from multiple cameras and lidars in real time and make decisions in milliseconds. The onboard computing platforms of companies like Tesla and Waymo heavily rely on GPU parallel computing power, and CUDA is the critical bridge connecting algorithms to hardware. The competitive landscape. CUDA isn't the only option, but the moat is extremely deep given CUDA's importance. Competition was inevitable. AMD's ROCm, an open computing platform for AMD GPUs, open source and supporting some CUDA code migration. IT has made significant progress recently and is becoming an option in some scenarios, but the ecosystem maturity still lags behind CUDA. Apple's Metal, Apple's GPU computing framework designed specifically for its own chips, M-Series, a series. It delivers excellent performance on Mac and iPhone but is locked inside Apple's ecosystem and cannot be used across platforms. Intel's One API. Intel's attempt to cover CPUs, GPUs, and FPGAs with a unified programming interface, an ambitious goal, but its market share in AI training remains small. OpenCL, a cross-vendor open standard that can run on NVIDIA, AMD, Intel, and other hardware. IT offers high portability, but performance optimization often falls short compared to vendor-specific solutions. And the development experience is relatively complex, so where is CUDA's moat? The answer is the ecosystem. Over the past decade, millions of AI researchers and engineers worldwide have written code, published papers, and built open-source projects using CUDA. Mainstream AI frameworks like PyTorch, TensorFlow, and JAX are all deeply adapted to CUDA. Almost every cutting-edge AI research implementation is first available on CUDA. This means, even if you develop a competing product with performance comparable to CUDA, you still face one major problem: getting the global developer community to abandon years of accumulated CUDA toolchains and codebases, then relearn and migrate. The cost is enormous. That's why, despite continuous efforts from AMD and Intel, NVIDIA continues to dominate the AI computing market, maintaining a market share consistently above 80%. Those invisible infrastructures are the true foundation of the era. Someone once asked, in the AI era, who makes money selling shovels? The answer isn't the model companies, it's NVIDIA. And CUDA is the sharpest blade on that shovel. IT doesn't have a user-facing interface that everyone can perceive like ChatGPT, nor an outwardly admired industrial design like the iPhone. IT lives deep in the code, inside server rooms, and in the logs of every model training run. Low-key, resilient, indispensable. The story of AI, on the surface, is about models, data, and algorithms, but the foundation holding all of this up is computing power, GPUs, and CUDA. The next time you say to an AI, write me a poem, you might silently thank those thousands of little elves in your heart, for in those fractions of a second of silence, they accomplished a computational miracle in human history. Every AI response is a silent symphony of computing power, and CUDA is the conductor. NVIDIA's share of the global AI chip market is 80 to 85%, with a gross margin of 75%. This isn't just simple technological leadership, it's the lock-in effect of a closed-loop ecosystem. 4 keywords: CUDA, developers, migration cost, system integration. NVIDIA's real moat isn't the chip itself, but the seed planted 20 years ago, the CUDA platform. Today, 4 million developers worldwide write code on this platform. Their models, toolchains, and optimization expertise are all bound to CUDA. Switching to a different chip means rewriting massive amounts of code and reaccumulating optimization experience. That's why, even if AMD's MI300X performs well in certain scenarios, or if Chinese-made chips boast impressive specs, market share still cannot be shaken from NVIDIA. Just how staggering is NVIDIA's monopoly? Let's look at a few numbers. Global AI chip market share, 80-85%. Gross margin, 75%, FY 2026. Annual revenue, $215.9 billion, net profit $120 billion. Top 50 global AI companies. 88% of computing power runs on NVIDIA chips. This isn't industry leadership, it's the industry standard. For comparison, Intel also held over 80% CPU market share in the PC era, but its gross margin was only 40-50%. NVIDIA's 75% gross margin indicates it's not just selling chips, it's selling an irreplaceable system. What's that system called? CUDA. What is CUDA? Why has it been able to monopolize for 20 years? CUDA, Compute Unified Device Architecture, is a platform NVIDIA launched in 2006. Simply put, it lets developers use a C++-like language to program GPUs for general-purpose computing, not just graphics. Back in 2006, this decision seemed pointless. GPUs were for gaming. Why make them do general-purpose computing? Jensen Huang's judgment was, the parallel computing capabilities of GPUs would eventually be found useful for many non-graphics applications. 16 years later, that judgment has been validated. The massive parallel computation required for training large language models is exactly what GPUs excel at. And CUDA had already accumulated 16 years of developer ecosystem key data. 2016, roughly 1 million CUDA developers worldwide. 2026, roughly 4 million CUDA developers, over 7.5 million registered developers, top 50 AI research institutions and companies globally, all using the CUDA platform. Those 4 million developers form NVIDIA's widest moat. You can compete by selling chips at a lower price, but these developers have been writing CUDA code for over a decade. Their models, toolchains, and optimization expertise are all bound to CUDA. The lock-in effect of CUDA. Why can't people switch? The lock-in effect manifests on 3 levels. Level 1, framework binding PyTorch, TensorFlow, TensorRT LLM. All mainstream AI frameworks have their optimal path on CUDA. When developers write code, the first line is often device equals CUDA. This isn't a matter of habit, it's about performance. The same model running on CUDA versus ROCm, AMD's alternative, can show a performance gap of 20–30%. Level 2. Toolchain ecosystem. CUDA is not just a programming tool, it's an entire ecosystem. CUDNN, deep learning acceleration, CUBLOS, linear algebra, TensorRT, inference optimization, NCCL, multi-GPU communication. Each component has over a decade of optimization behind it. AMD's ROCm is catching up, but the maturity of libraries, documentation, and community support still lags significantly. Level 3. Migration cost. A team that has written several sets of algorithms in CUDA has all its engineering experience stacked on that framework. Switching to another chip means rewriting massive amounts of code, retuning performance, retraining the team, reaccumulating optimization experience. The cost is simply too high. So even if AMD's hardware offers better price performance, developers have no incentive to migrate because CUDA is already good enough. NVIDIA's 4 layers of barriers. CUDA is only the first layer. NVIDIA's monopoly is the result of 4 overlapping barriers. First, leading chip performance. The B200 GB200 currently leads competitors by approximately 1.5–2x in FP16 and FP8 compute performance. Part of this lead comes from priority access to TSMC's most advanced process. NVIDIA usually secures first batches of capacity, and part comes from long-term accumulation in GPU architecture design. Second, the CUDA software ecosystem. 4 million developers, 20 years of accumulation. This is the widest moat. Third, NVLink interconnect technology. AI training isn't a single card battle, it's thousands or tens of thousands of cards working in concert. The interconnect bandwidth between GPUs becomes a critical bottleneck. NVIDIA's NVLink 5.0 achieves 1.8 terabytes per second bandwidth, significantly outpacing competitors' interconnect solutions. This gives NVIDIA's multi-GPU training efficiency a 30–50% advantage over rivals. Fourth, system integration capability. NVIDIA now sells not just chips, but entire AI factory systems. The GB200 NVL36 server rack costs $1.8 million per unit, the NVL72 costs $3 million. These systems contain GPUs, CPUs, networking chips, and the NVLink architecture, all packaged together. Customers aren't buying a component, they're buying a turnkey computing platform. Why can't competitors catch up? The 4 overlapping barriers create an extremely strong lock-in effect. AMD's MI300X performs well in some scenarios, and may even offer better price performance. But the migration of the developer ecosystem takes time, and many developers simply have no motivation to switch. Google's TPU and Amazon's Trainium are proprietary chips, but they primarily serve their own cloud businesses and aren't sold externally, so they can't shake NVIDIA's position in the open market. Chinese-made chips, their hardware performance lags by about 2 to 3 generations, and the software ecosystem is even more fragmented. Huawei has CAN, more Threads has Musa, each carving out its own territory. Developers adapting to domestic cards often need to rewrite code. According to a 2026 Goldman Sachs analysis report, approximately 88% of AI training compute among the world's top 50 AI companies runs on NVIDIA chips. That proportion is unlikely to decrease significantly in the foreseeable 3 to 5 years. NVIDIA's next step, from cloud to desktop. NVIDIA hasn't stopped. In June 2026, Jensen Huang did 2 things in Taipei. First, put CUDA into laptops. The RTX Spark laptop features a 20-core ARM CPU plus a Blackwell GPU with 6,144 CUDA cores, 128 GB unified memory, 1 petaflop of AI compute, and is just 14 mm thick. This means CUDA code developers write in the data center can run directly on a laptop without changing a single line. Qualcomm's Snapdragon X and Apple's M series don't have CUDA. Second, bring trillion-parameter inference to the desk. The DGX Station desktop, based on GB300 chips, can run models up to 1 trillion parameters locally, priced between $80,000 and $125,000, launching Q4. Risk models for financial institutions, contract reviews for law firms, medical imaging analysis for hospitals. These workloads can be handled with a single desktop machine. No more cloud computing bills needed. NVIDIA is expanding its toll booths. Previously it only earned money from cloud providers. Now it wants to earn from enterprise desks and developer laptops. NVIDIA's monopoly isn't just good chip performance, it's the lock-in effect of a closed-loop ecosystem. CUDA, 20 years of accumulation, 4 million developers, framework binding chip performance, 1.5-2x lead over competitors. NVLink, 30 to 50% multi-GPU. Synergy efficiency lead. System integration. From selling chips to selling AI factories for competitors to catch up, they would need to break through all 4 barriers simultaneously. In the short term, it's nearly impossible. But there's one variable: export controls. The US restrictions on high-end chip exports to China are forcing domestic alternatives. Can Huawei ascend, High-Gone DCU, more threads, and other Chinese chips break through? NVIDIA is actually a software company. Please forgive me for starting with an overused financial term that has recently crept into the tech vocabulary. I'm afraid I must discuss the moat. Decades ago, Warren Buffett popularized this term to refer to a company's competitive advantage. Later, an alleged leaked Google memo titled "We have no moat, and neither does OpenAI" worried that open-source AI would destroy big tech's fortresses, and since then, the term has appeared in Silicon Valley pitch decks. Several years on, the castle walls remain sturdy. Apart from the brief panic caused by DeepSeek's emergence, open-source AI models have not significantly outperformed proprietary models. Yet none of the frontier labs, OpenAI, Anthropic, or Google, have formed a true moat. The company that truly possesses a moat is NVIDIA. Its CEO, Jensen Huang, calls it his most precious treasure. But for a chip company, the treasure isn't the hardware you'd expect. It's a technology called CUDA. This name, which sounds like a chemical banned by the FDA, may very well be the real moat in artificial intelligence. Technically, CUDA stands for Compute Unified Device Architecture, but much like laser or scuba, nobody bothers to spell out the acronym. We just say CUDA. So what does this vital technology actually do? In a single word: parallelization. Consider a simple example. Suppose we ask a machine to fill out a 9 by 9 multiplication table on a single core computer. All 81 operations are executed one by one, but a GPU with 9 cores can distribute the work, assigning each core to a different column. One handles 1 by 1 through 1 by 9, another handles 2 by 1 through 2 by 9, and so on, achieving a 9-fold speedup. Modern GPUs can be even smarter. For instance, if programmed to recognize commutativity, 7 times 9 is equal to 9 times 7, they can avoid redundant work, reducing 81 operations to 45, nearly halving the workload. When a single training run can cost $100 million, every optimization matters. NVIDIA's GPUs were originally designed to render graphics for video games. In the early 2000s, a Stanford PhD student named Ian Buck, who initially became interested in GPUs through gaming, realized that the GPU's architecture could be used for general high-performance computing. He created a programming language called Brook and was later hired by NVIDIA, where he co-led CUDA's development with John Nichols. If AI truly ushers in an era of a permanent white-collar underclass and autonomous weapons, know that it all started because someone playing Doom had the idea that demon scrotums should jiggle at 60 frames per second. CUDA itself is not a programming language but a platform. I use that word because, just as the New York Times is both a newspaper and a gaming company, CUDA has evolved over the years into a nested collection of AI software libraries. Each function saves maybe a few nanoseconds on a single math operation, but added together, they make GPUs go BRR, in industry parlance. A modern graphics card isn't just a circuit board stuffed with chips, memory, and fans. It's meticulously crafted with cache hierarchies and specialized units called tensor cores and streaming multiprocessors. In that sense, what a chip company sells is like a professional kitchen, and more cores are like more grilling stations. But even a kitchen with 30 grilling stations won't run faster without a skilled head chef intelligently delegating tasks, much like CUDA does for GPU cores. Taking it further, The hand-tuned CUDA libraries optimized for single matrix operations are like kitchen gadgets that do only one thing, say, a cherry pitter or a shrimp deveiner, nice to have for a home cook, but a sheer waste if you're deveining tens of thousands of shrimp. This brings us to DeepSeek. Its engineers pierced through what was already a deep layer of abstraction and coded directly in PTX, an assembly language for NVIDIA GPUs. Imagine the task is peeling garlic. An unoptimized GPU might issue, use your fingernail to peel the skin. CUDA could issue, crush the clove with the flat of a knife. PTX, meanwhile, lets you define every subinstruction, raise the blade 2.35 inches above the cutting board, parallel to the clove's equator, then strike downward with the palm at 36.2 newtons of force. By now you should understand why CUDA is so crucial to NVIDIA and so elusive for others. GPU performance tuning is a dark art. You can't just grab some guy loitering on Market Street, hand him a Claude Max subscription, and expect him to crank out GPU kernels. Writing that level of code is an immensely demanding task unless you're a top-tier programmer at DeepSeek. In previous machine-readable columns, I've been quite familiar with the languages under analysis. Not this time. To maintain that standard, I decided to spend a day learning CUDA. I ended up burning an entire afternoon in PyTorch, a popular machine learning framework. A simple matrix multiplication often takes just 3 lines of code, but in CUDA it takes over 50. As it turns out, squeezing out every last drop of performance is an admirable yet excruciatingly tedious endeavor. Having dipped my toes in, I can responsibly say that this moat is indeed impossibly deep. CUDA's dominance is built not only on the superior quality of its ecosystem but also on powerful vendor lock-in. Because modern machine learning frameworks are built atop CUDA, and CUDA primarily runs on NVIDIA chips, even when AMD's chips pack more cores and video memory, their real-world performance still falls short. Comparing chips solely by spec sheets is like comparing race cars solely by cylinder count. The real performance only reveals itself on the track. A second point, I had intended to test both chips, but purchasing both an NVIDIA H100 and an AMD MI300X would surely get me blacklisted by Condé Nast, so you'll have to take the word of independent researchers, who found that even when AMD's on-paper specs were better, actual performance lagged behind NVIDIA. NVIDIA's software edge may stem from the fact that, unlike other chip companies, it employs more software engineers than hardware engineers. If I were running AMD, I'd probably follow suit. Though who would ask me? Every year, new challengers try to breach NVIDIA's moat, only to be swallowed by it. OpenCL, an open standard backed by a consortium including Apple, AMD, and Qualcomm, is essentially the failed Android to CUDA's iOS, gaining virtually no traction. Meanwhile, AMD's answer to CUDA, ROCm, bears an even worse name than CUDA. Is it meant to be pronounced ROCm? Don't bother hiring more programmers, replace your marketing team instead. ROCm is also plagued by bugs and compatibility issues, to the point where its subreddit looks like a help forum. Let's not forget Intel. While it's easy to dismiss them as a fading chipmaker, their recent history shows they're also a fading software company. In a bid to save face, they launched one API, but by 2026, we can be pretty sure CUDA still dominates. If there is a challenger, it's Modular, led by Chris Lattner, the legendary language designer behind Apple's Swift and LLVM. But the open secret is that, much like theoretical physicists who can't change a tire, most AI researchers can't write a single line of C++. Excellent GPU kernel engineers are few, and many of them work at NVIDIA. Long before AI researchers began monopolizing their influence, these engineers were quietly toiling away on CUDA. Even the most trusted coding assistants still stumble when writing kernel code. Ultimately, NVIDIA is perhaps more akin to Apple than to AMD or Intel. It's a great hardware company because it's fundamentally a software company. Apple's moat against Android was never just the iPhone, it's the entire ecosystem. iOS, the App Store, and its developers. Sure, you can fold a Samsung Galaxy in half, but do you really want to use Samsung Pay? Meanwhile, the rest of the industry will likely have to endure NVIDIA's high prices for the foreseeable future.